most cells of the body are going to be sensitive to more than one hormone. How can that be? Example, growth hormone, thyroid hormone, muscle cells. Are muscle cells sensitive to both? Yes. Why? These are two hormones that are constantly produced, and their job is affecting basically nutrient usage and metabolism of the cell. And we need both for that cell to function correctly. So it's going to be sensitive to more than one hormone. And it'll be sensitive to other hormones too, other chemicals also. So when these cells have sensitivity to more than one hormone, effects can come about for that cell. What does it mean to be synergistic? Synergy?
Exactly.
Oh, we're all working together. Yay! Synergy for me. Okay, so we're all working together. So there could be 1, 2, or more hormones, and we get a greater effect by being sensitive to more. Good example, FSH and testosterone acting on sperm production. Permissive. What do you think of? Huh?
Permission.
Permission. It's giving me permission to do something. What else about permissive?
I kind of think of passive.
And is that opposite of passive?
I kind of think of permissive as,
I think a gate, like you can enter, you're allowed to come through the gate or something.
I kind of think of it as like, you know, okay, well, come on, let's try this, you know? So permissive would be one of those chemicals enhance that target organ, target tissue's response to something that's going to come along later. Okay? Sort of like, okay, well, here I am, I'm the first hormone, and that hormone's going to be the second hormone. I'm going to give you permission to come to this organ. But you don't get to be here till after me. So, good example. Estrogen prepares the uterus for the action of progesterone. Working together, they would want to be preparing that for the income of the fertilized egg. And if the egg doesn't get fertilized, what happens to that lining? We shed it. Menstruation. How about antagonistic? Oh, they're opposite. Total opposite effects. They're opposing each other's actions. Insulin lowers blood glucose, but glycogen, because we have the glucagon that can act, okay, will raise it. So the hormones have different or they can be, the cells can be sensitive to more than one, but depending on what the hormones are, will determine what's the action going to be. Once we have the hormones in the system, we have to make sure, for the most part, that signals that got that hormone started get turned off. The body, for the most part, is going to take the chemicals that have hopefully been used, produced correctly within the body, get it to the liver or the kidneys, but break it down. Degrade that chemical so that that chemical is no longer active. So a lot of it we excrete in bile or urine. So we either urinate or it comes out in the feces. So that's the hope, as long as things are working correctly. We do have something called a metabolic clearance rate. Basically, what is the rate that it takes to remove that particular chemical from the blood? We mentioned the half-life, okay? So the half-life, what does it take to clear 50% of that chemical out of the system? The faster the clearance rate, the shorter the life is. A good example.
Sorry, is that supposed to be NCR?
Yeah, I just noticed the typo. Thanks for correcting that.
Sorry, just wanted to make sure.
And I noticed one in 18 when I went back and looked at it, but I already printed those out, but that's okay, we'll fix it. Good example, growth hormone. Doesn't use any type of transport protein, so it's flying around in the blood free. When we look at the half-life, it only has a half-life of about 20 minutes for the growth hormone. So that's not long at all. So the quicker we can get it out of the system, all right, the shorter the time that we actually have it in use in the body. Some of this is good because we don't need to have but so much of that action on the cell.
Why do we care about the half-life? Like, why don't we measure it by how fast all of it is gone?
When we talk about chemistry, okay, and since we're looking at these chemicals, chemistry and chemicals is based on what is the half-life of a chemical. So in chemistry, that's how they pretty much look at everything you see on the periodic table. Everything's going to have a half-life, because after that, that remaining 50%, there'll be a half-life of that 50%. And then after that, there'll be another half-life of that remaining, until basically you get down to where it's nothing left. So the chemists are for the reason. The chemists are the reason for half-lives. Just saying. But biologically, maybe we look at it that way based on the action it can have on the cells. So if we decrease the action by half, we only have to worry about another decrease in half. Once we've done that, we've technically cleared 75%. So the half-lives are kind of short. Chemicals, on the other hand, can have half-lives of thousands of thousands of thousands of years. Luckily for us, none of that should be in our body. One of the things that happens with the chemicals, the hormones, do you guys remember me kind of pointing out stress? Because your book seems to emphasize stress, okay? The stress response. And I kind of said that one of the things about stress, there's good, there's bad, but it's still stress, all right? And then mentioned how if there's a prolonged stress, it can kill you. So according to, because in your textbook, it spends quite a bit of time talking about the stress response. and it puts it into 3 stages for the stress response. And it refers to stress as being anything that disrupts homeostasis. So if we have anything that's going to disrupt homeostasis, it is considered a stressor. Whether it's the fact that you might be exercising, it's a stressor that disrupts homeostasis. So we're going to react to stress from our nervous system and the endocrine system both. The first stage that's classified as a reaction to stress is called the alarm reaction. The alarm reaction and the 3 stages all together. The way that we react to stress, pretty much we react to it in a fashion that's the same all the time. So whether we're thinking about it being that good stress or the bad stress, we tend to go through these 3 stages no matter what. Okay? Maybe not long, might be very short-lived, but anyway, when we have that alarm reaction, the first, looking at this particular stage, the stress response usually or always is going to give us norepi and epi. Do you guys remember yesterday how I talked about the norepi coming from that sympathetic nerve fiber to the adrenal gland, synapsing with the cell, and then that cell produces epinephrine? Do you guys remember that? Okay, so the alarm reaction, when this occurs, when that sympathetic nerve fiber synapses with the cell in that adrenal medulla gland, okay, that epinephrine begins to prepare us for fight or flight. We're going to see that because the body has now moved into the fight or flight mode, we got to make sure we supply it with energy. So we're going to take glycogen stores, pull that glycogen out, convert it to glucose, and use it for energy. We're then going to see that it will increase aldosterone and angiotensin. Why? What in the world? Now, give me some examples of when we might be in a stress situation other than physical exercise. What else could...
Chasing you.
Somebody's chasing you?
Exams.
Huh?
Yeah, like exams coming
Okay, exams.
A fire.
A fire.
Fear.
Fear. How about if we're shot, stabbed, broken bone, accident, wreck, whatever? These 2 right here, because aren't those stresses? I don't know about y'all, okay, but I'm pretty sure if I were to get shot, I'd be stressed. If I was still here, just saying.